And the same will be true for this. We will not give a special name. We will discuss later on why, but we don't give a special name. This also maps Tn into Tn. And the same for A0. A0 is also this remark that A0J, in fact, let me say, A0 is, notice that A0 is self-adjoint by construction, because P is Hermitian projection, and X is self-adjoint, is Hermitian itself. Okay? So, A0 is Hermitian, and therefore A0 is uniquely determined by its restriction on Pn, which we have denoted with the symbol A0 bar n, vertical bar n. Now, let us pose the problem that we want to solve. What is the problem? If you remember, using the fact that all these Pn are one-dimensional, in the case of one dimension, we have this operator becomes the multiplication by a number. And in this case, j equal k. When j equal k, this is a positive operator, so the number must be positive. But here we have not. We have not. If the space V is isomorphic to Rd, then the indices j and k vary in 1 and d. So this is an operator. But when we restrict this operator to n, we have a matrix. So bar n means restriction. Remember, in our notation, bar n, vertical bar n means restriction. So if we restrict, this is a space with a large dimension but finite. So this is a matrix. This omega jk is a matrix. And depends on two indices. So we have a matrix whose coefficients are a matrix. This is means that, moreover, these are adjointable and this is adjointable, and we know that the product is adjointable. So we have that the kernel omega j, we call a kernel something that is depends on two indices. A kernel is a generalization of a matrix. The point is that the two indices can be arbitrary, and it's very useful in mathematics to take a general point of view on kernels. So this omega is a kernel, but where it takes values? It takes values in the linear adjointable operators of P. Be considered as a pre-Hilbert space, so let us write this so you remember that I am considering P as a pre-Hilbert space. Phi0 is the identity, so as I said, they are the same. Okay? Now, but this kernel has a very important property. Why? What is this property? Well, this is, now I will speak of orthogonal polynomial, but if you remember our lecture on interacting Fock space, you will notice that what I am saying is true for any interacting Fock space. Okay? So what is the point? I know that if I apply a vector AV to a polynomial of degree, orthogonal, an element of the orthogonal polynomial of degree n, and I do the same for another. Well, let us do for jk. Remember that AJ means AEJ, and AK means AEK, applied to a certain vector. This in the space n+1, because we are applying creator to something of degree n. Okay? But since I have the adjointable relation, this I will write as Cn A minus Ej A dagger Ek in eta n. And now I am in the scalar product in the n particle space, the n orthogonal polynomial space. So, but this is what? This is exactly our kernel. Remember our definition. So this is omega. This is but in fact is omega restricted to the n particle space. So I can use the restriction, because remember the remark that we did for A0 is true for any gradation preserving operator. If I have an operator which is gradation preserving, it is uniquely determined by its restriction on all Pn. And so it's uniquely defined by a sequence of matrices. Okay? But here I have not an operator on Pn, but I have a kernel which is in this space, and from this proof, what we can deduce? We deduce that omega n restricted, omega jk restricted to n belongs to the linear adjointable operators of Pn. Pn is not necessarily phi because it's by definition it is a space.
So when you say kernel, you mean this positive definite?
It's even more completely positive there. You can prove. It's an easy
Pn.
Of course, you have to generalize a little bit because usually the definition of complete positivity is given for C star or W star algebra. So here we are speaking of a general star algebra, but you give the same definition. You say that if a map P is completely definite if and only if for each the map P tensor identity n, where E is the identity map on the n by n matrix. For each n is possible. The definition is the same. Nothing will change. Of course, we have not such a richer, but I think also there should be no difficulty. Well, to prove, for example, some Stein-Spring theorem for star algebra. I don't know. The completely positive maps on general star algebra have not been very much studied. It may be for our, since we continuously use, but we don't need a general theory because we have always very concrete objects. So we prove the theorems for the object we need. But of course, if there is a general theory, it's better. So this is a, for example, the dimension of this space, if I remember well, which we call dn by definition, is something like n plus d minus 1 is the same dimension as the space of as the symmetric tensor power of CD, the nth symmetric tensor power of CD. So you make a simple combinatorial calculation and you find what is the dimension of this space. And you see asymptotically this will go like n to the t minus 1 for large n. So you understand why D is the critical dimension. The just D minus n should be 0. I don't know why 0 and not 1, but it should be well. Let us now arrive to the point, because I see that the time I have only 2 minutes. So what we want to do now, I will not, because now the calculation begin to be a little bit involved. So, but I want to explain what is the root of what we want to do. We want to prove a reconstruction theorem. You remember that the reconstruction theorem we proved in one dimension, Favard lemma, was given omega n and alpha n, how can we construct a state on the polynomial algebra? Now, all this discussion is aimed at showing that the analog of omega n in one dimension will be this kernel. The family of kernels, which is the same as the operator kernel. So J and K go from 1 to D, and N is arbitrary integer. And the analog of alpha N will be A0J restricted to N. And the problem is, we want to show, but here will be more difficult. In the one-dimensional case, life was a little bit easier. But here we have what we exploit. We exploit the same idea that we had in one dimension, but the difficulty comes from this, because this will pose constraints on our reconstructions. So we have to be sure that our reconstruction respects these constraints. So what we will do, we will use the quantum decomposition that I wrote somewhere, this one. And as we did in one dimension, we will write the same quantum decomposition in the form that well, let us write directly a J, because we work on the basis now. So you see, the crucial point is that we expect that, like in the classical case, this should be arbitrary. Unfortunately, it will not be true. The alpha n are arbitrary, but here they are not arbitrary. There will be constraints coming from this, from these two relations. And what it took a lot of time to understand is that this relation follows from the combination of the two. But this is more involved. Now, the important point is that you see the point is this. Conceptually, this is the most important point. So we want to use this. This is roughly speaking the analog of the omega n. And this is roughly speaking the analog of the alpha n. And then we use this inductively. That is, instead of writing this as on the infinite dimensional space, we write it on the restriction. on the n-dimensional space. So on the 0 dimension, this is 0. This acts as a single number, and I choose arbitrarily this number. And this is given because it's multiplication by xj, which is algebraic. So I can define the creation of 0. And then I proceed inductively. Having defined, suppose that I have defined the creation on all k less or equal than n, and I have chosen the I0 k for all k less or equal than n, and I have defined a daga k for all k less or equal than n, this is already said. Then, since xj is algebraic, sjn is always defined, and I can define a daga. And now, in order to a plus jn, but in order to define a minus jn, I need the scalar product on n plus 1, because the range of a daga is on n plus 1. Here, I will exploit my arbitrariness, but I have to respect the constraints. Once I have the scalar product, I have a minus. See, of course, I exploit here the fact that I have to choose this. This will not be arbitrary, but how do I remember? These are matrices. Some of the coefficients will be arbitrary. What is an open problem that we really would like to understand, which is exactly the arbitrariness of the free parameters? Can we control this? This is you will see the problem of linear algebra. So it should be solvable.